Design of typical summer air conditioning system. Suppose that a room which has to be maintained at room design conditions of dBT is equal to 25 degrees centigrade and RH is equal to 50%. They are the human comfort conditions. So a room has to be designed for the sake of the occupants, which may be for the sake of office room, or which may be a theater, or whatever it is. The occupants need the comfort conditions of 25 degrees centigrade relative temperature and 50% relative humidity. This has to be maintained all the time, and for which how much is the necessary of room supply air we would have to see, and at what temperature we have to supply the room supply air we have to see. First of all, before designing the system, we will have to estimate, we will have to calculate what is the total heat that has to be handled by the room supply air after entering into the room. That means how much total heat load is developed within the room because of the solar influx heat, because of the heat evolved from the persons, because of the heat evolved from the electrical equipment like bulbs, fans, etc. that are present in the room. Like this, we have to estimate, we have to calculate what is the total room heat load inside the room. So first of all, let me draw what is the typical flow diagram of the air conditioning system. This is recirculated air. This is outside air. This is room supply air. Sorry, this is mixture. Mixture of outside air and recirculated air. This is AC cooling coil or dehumidifying coil, inside which refrigerant liquid enters, and after picking up the heat, the refrigerant vapor leaves the coil in the dry saturated state. So the flow diagram goes like this. State 1 is the room design condition or RD condition is 1. Outside ambient air, outside or ambient air state is state 2. This is 2. So the recirculated air, approximately 60% at the room design condition, mixes with the 40% of the outside air which is there at state 2 to form the mixture state at 3. This mixture of recirculated air and outside air shall be passing over the air conditioning cooling coil or dehumidifying coil, which is there at a temperature of ADP. The surface temperature of the AC cooling coil is called as apparatus dew point, abbreviated as ADP. And after getting cooled and dehumidified over the coil, it leaves at the state 4. It leaves the coil at state 4, which is supposed to be room supply air. The flow diagram is drawn. Now the corresponding psychrometric processes are shown on the psychrometric chart. This is dBT, W, specific humidity, kg of water vapor per kg of dry air. State 1 is the room design condition. State 2 is the outside air. Both are mixed to obtain state 3. This is an adiabatic mixing, that mixture of room supply air, mixture of air, not room supply air, mixture of air, which is passed over the AC cooling coil So state 4 will be the room supply air, which will be entering into the room and picks up the heat from the room. So room design air mixes with the outside air to form state 3, that is a mixture air, which passes over the AC cooling coil where it gets cooled and dehumidified. This is ADP state, apparatus dew point. State 4 is the room supply air. So when the mixture air at state 3 passes over the AC cooling coil having the temperature of ADP, this air gets cooled and dehumidified. So 1 to 2 process is adiabatic mixing of RD room design air and outside air to get state 3. 3 to 4 is cooling with the dehumidification of mixture of air, that is recirculated air and outside air. 3 to 4 is cooling with dehumidification of mixture of air as it passes over dehumidifying coil or AC cooling coil. I can say that noting the state 5 as apparatus dew point. The gap between 4 and 5 will indicate the bypassing of the air as it passes over the cooling coil. And state 4 to state 1, this is a process of heat pickup by the room supply air after entering into the room. So there are totally 3 psychrometric processes in this system. Number 1, adiabatic mixing of room design air or recirculated air with the outside air to get state 3. Three to 4 is a cooling with the dehumidification of this mixture of state 3. So resulting in state 4. 3 to 4 is cooling with the dehumidification where air gets cooled and as well as dehumidified. Process 4 to 1 is the heat pickup by the room supply air after entering into the room from the occupants, from the things that are present inside the room. Process 4 to 1 is heat pickup by room supply air after entering the room from the occupants and the things that are present in the room. So representing this process, that is 4 to 1, is actual psychrometric process corresponding to the heat pickup by the room supply air taking place within the room. If you draw a horizontal line here, you get x. Draw a vertical line from 1 to intersect at x, indicating the enthalpies H1 on the enthalpy scale. This is H4, this is Hx. Hx minus H4 is room sensible heat load. H1 minus Hx is equal to room latent heat load. This is abbreviated as RSHL or LHL. Room sensible heat factor is equal to room sensible heat load divided by room sensible heat load plus room latent heat load. This is RSH, this is RLH. W is kg of water vapor per kg of dry air. What do you mean by room sensible heat load? Room sensible heat load, abbreviated as RSHL, is the heat that is picked up or received by room supply air after entering the room, which is manifested by the increase of dry bulb temperature alone without any change in specific humidity. So in the RSH or room sensible heat, the heat that has been taken by the room supply air because of the temperature difference between the room occupants from the things that are present in the room and the room supply air. So because of delta T, because of the temperature difference, if any heat is picked up by the room supply air, it is called as room sensible heat load, which it is manifested by the increase of dry bulb temperature alone. If 4 to x is a horizontal line, wherein no change of specific humidity is observed. Similarly, RLHL is the heat that is picked up by room supply air after entering the room, which is manifested by the increase of specific humidity alone without any change in dBT. So RSH or LHL is a heat load picked up by the room supply air, because of which the humidity of the room supply air alone is increasing without any change in dBT. So this is called room latent heat load. Room total heat load is room sensible heat load plus room latent heat load. Room sensible heat factor is defined as the ratio between room sensible heat load and the room total heat load, which will be approximately 0.7 or 0.75. Usually the values of RSHF, room sensible heat factor, will be around 0.7 or 0.75. That means out of the total heat load that is to be handled by the room supply air after entering into the room, approximately 25% will be the latent heat load and 75% will be the sensible heat load. If we take the persons sitting inside the room, the persons or occupants shall add both sensible and latent heat loads, because the persons will have sweating or perspiration. When the sweat evaporates, the humidity content of the room will increase, and they will add the sensible heat also because of the temperature difference between the human body and the surrounding air. Whereas the electrical equipment like bulbs, fans, any heaters, etc., shall add only sensible heat, because they would not release any sweat. So they add only sensible heat load. Whereas solar heat conducted through walls shall add sensible heat only, because it is a heat conducted through the walls from outside into the room, from the glass panes, from the outside walls. The heat will be conducted and convected into the room. This is contribute to the sensible heat of the room. After drawing room sensible heat factor line on the chart, passing through room design state, we shall obtain room supply air condition H4. Hence, the mass of air supplied into the room per minute is equal to total room heat load in kilojoule per minute divided by heat picked up by 1 kg of room supply air, that is H1 minus H4. You will obtain in kg per minute. This is how the mass of the room supply air per minute flowing into the room could be calculated. Now I shall solve a problem given in GATE 2006. The statements concern psychrometric chart. Number 1. Constant relative humidity lines are uphill straight lines to the right. Number 2. Constant wet bulb temperature lines are downhill straight lines to the right. Number 3. Constant specific volume lines are downhill straight lines to the right. Number 4. Constant enthalpy lines are coincident with the constant wet bulb temperature lines. Which of these statements are correct? A. 2 and 3, B. 1 and 2, C. 1 and 3, D. 2 and 4. Now look at the first one. Constant relative humidity lines are uphill straight lines to the right. That is absolutely wrong. In fact, constant RH lines are curves. Number 2. Constant wet bulb temperature lines are downhill straight lines to the right. That is absolutely correct. If you draw the psychrometric chart, this indicates the constant WBT line. WBT1 is equal to constant, W2 is equal to constant. If you look at the state 4, Constant enthalpy lines are coincident with the constant wet bulb temperature lines. That is also correct. Statement D is right, because constant enthalpy lines will be coinciding with the constant WBT straight lines, which are straight lines to the right, sloping right. This is psychrometric chart. So answer is D. Now let us solve a problem given in GATE 2007. Atmospheric air at a flow rate of 3 kg per second on dry basis enters a cooling and dehumidifying coil with an enthalpy of 65 kilojoule per kg of dry air and a humidity ratio of 19 grams per kg of dry air. The air leaves the coil with an enthalpy of 43 kilojoules per kg of dry air and a humidity ratio of 8 grams per kg of dry air. If the condensate water leaves the coil with an enthalpy of 67 kilojoule per kg, the required cooling capacity of the coil in kilowatts is A 75.0, B 123.8, C 128.2, D 159.0. The solution to this problem could be given like this. There is a dehumidifying coil. Air is entering moist air at state 1, where the enthalpy H1 is 65 kilojoule per kg of dry air and leaving enthalpy H2 is 43 kilojoules per kg of dry air. This is dehumidifying coil or AC coil. Representing the thing over the psychrometric process, the process goes like this. This is state 1, this is state 2. This is H1, 65 kilojoules per kg of dry air. This is state 2. 43 kilojoules per kg of dry air. This is dBT. This is W. What is the mass flow rate of the air? Mass flow rate of the air is 3 kg per second. This specific humidity W1 is also given, that is 19 by 1000, that is 0.019. This is W2 is given as 0.008. This is a cooling with dehumidification process. The capacity of cooling and dehumidifying coil is equal to mass flow rate of the dry air into H1 minus H2. Mass flow rate of the air is given as 3 into 65 minus 43. This is 3 into 22. I'm sorry, this the inlet enthalpy is given as 85. Correct, making that correction. This is inlet enthalpy is 85. Please make the correction that inlet enthalpy of air entering the coil is 85 kilojoule per kg of dry air. 3 into 42, it comes to 126 kilowatts. The answer would be 126 kilowatts. Now I shall do a problem in GATE, given in GATE 2003. For air with a relative humidity of 80%, comma, A. The dry bulb temperature is less than the wet bulb temperature. B. The dew point temperature is less than wet bulb temperature. C. The dew point temperature and WBT are equal. D. The dry bulb and dew point temperatures are equal. Because the RH is less than 100%, it means the air is unsaturated. Since RH phi is less than 100%. Hence, for unsaturated air, dry bulb temperature is more than wet bulb temperature, which is more than dew point temperature. The answer is dew point temperature is less than WBT. B is the answer. Now I shall do a question, objective question given in GATE 2004. environment friendly refrigerant R134A is used in the new generation domestic refrigerators. Its chemical formula is A CHClF2, B C2Cl3F3, C2Cl2F4, D C2H2F4. Based on the formula, we could, based on the code, that is R134A, solution is like this. Code is given as R134A. First digit is equal to number of carbon atoms minus 1. Therefore, implies C is equal to 2. Second digit is equal to number of hydrogen atoms plus 1, implies H is equal to 2. Third digit is equal to number of fluorine atoms. Therefore, the answer is, it is an ethane based. There are 2 carbons and 2 hydrogens and 4 fluorines. No chlorine in this. So answer is C2H2F4, D. Why it is called environment friendly? Because it does not deplete this refrigerant, does not deplete ozone layer present in the stratosphere of the atmosphere. Hence it is called environment friendly, used in the new generation domestic refrigerators. Now I shall do another problem given in GATE 2004 on air conditioning. The problem is given like this. Dew point temperature of air at 1 atmospheric pressure, that is 1.013 bar, is 18 degrees Celsius. The air dry bulb temperature is 30 degrees Celsius. The saturation pressure of water at 18 degrees centigrade and 30 degrees Celsius are 0.02062 bar and 0.04241 bar respectively. The specific heat of air and water vapor are respectively 1.005 and 1.88 kilojoule per kg Kelvin, and the latent heat of vaporization of water at 0 degree centigrade is 2500 kilojoule per kg. The specific humidity in kilojoule per kg of dry air and enthalpy in kilojoule per kg of dry air of this moist air respectively are A 0.01051, 52.64, B 0.01291, 63.15, C 0.01481, 78.6, D 0.01532, 81.40. The solution to this problem is given like this. What is the formula for finding out specific humidity or humidity ratio W? 0.622 into PV by PB minus PV. This is the formula for W or specific humidity, kg of water vapor per kg of dry air. They are the units of W. Here PB, the total barometric pressure, is equal to 1.013 bar. It is given. What is PV? PV is partial pressure of water vapor, or it is the saturation pressure corresponding to dew point temperature from tables, from steam tables, which is given in the data itself. If you look at PSAT versus TSAT, PV corresponding dew point temperature, PS will correspond to the dry bulb temperature. Here the saturation pressure of water at 18 degrees centigrade, dPT, is given as 18 degrees centigrade, implies saturation pressure is 0.02062 bar, implies W is equal to 0.622 into 0.02062 divided by 1.013 minus. So this is the answer for W, kg of water vapor per kg of dry air. Coming to the enthalpy of moist air, which is given as in kilojoules per kg of dry air as 1.005 into TdB plus W into 2500 plus 1.884 into TdB, kilojoules per kg of dry air. Substituting the values, dry bulb temperature is 30 degrees. You have to substitute only in Celsius. W is already obtained above. 2500 plus 1.884 into 30 degrees centigrade. So many kilojoules per kg of dry air. The answer would be 63.15. W answer would be 0.0129. So answer is B for the question. Next, the problem is given from the GATE 2005. The problem is given like this. Various psychrometric processes are shown in the figure below. The figure is given like this. Zero to 1, 0 to 5, 0 to 4, 0 to 3, 0 to 2. kg of water vapor per kg of dry air, that is specific humidity, and dBT is given in centigrade. The question is given like this. Process in figure. Name of the process. P is given as 0 to 1, Q is given as 0 to 2, R is given as 0 to 3, S is given as 0 to 4, T is given as 0 to 5. Right side, number 1, chemical dehumidification process. Number 2, sensible heating. Number 3, cooling and dehumidification. Number 4, humidification with steam injection. Number 5, humidification with water injection. From this we can have to match the things. 0 to 1, that is obviously horizontal process. It should be sensible heating. So P matches with 2. 0 to 2, that should be the chemical dehumidification process. wherein the WBT remains constant and enthalpy also remains constant. Looking at the 0 to 3, that is cooling with the dehumidification process, that is R corresponds to 3. Going with the 0 to 4, that is the adiabatic humidification, which can also be called as humidification with the water injection. Going with 0 to 5, that is T, process T, there the dBT is increasing, W is also increasing. It is humidification with the steam injection. So P matches with 2, Q matches with 1, R matches with 3, S matches with 5, and T matches with 4. That is the answer. Now I shall do a problem given in GATE 2006. A thin layer, the problem is given like this. A thin layer of water in a field is formed after a farmer has watered it. The ambient air conditions are temperature is 20 degrees centigrade and relative humidity is 5%. An extract of steam tables is given below. Temperature, degrees centigrade, that is saturation. -15, -10, -5, 0.01, 5, 10, 15, 20. Pressure in kilopascal is given 0.10, 0.26, 0.40, 0.61, 0.87, 1.23, 1.71, 2.34. This is the extract of steam table given along with the problem. Neglecting heat transfer between the water and the ground, the water temperature in the field after phase equilibrium is reached equals A 10.3 degrees centigrade, B minus 10.3 degrees centigrade, C minus 14.5 degrees centigrade, D 14.5 degrees centigrade. The solution to this problem is given as: once the phase equilibrium is reached between surrounding air and water surface, the temperature of air, the temperature of water would be equal to dpt of air. How to get the dpt of surrounding air? dpt is dpt is Tsat at PV of vapor, PV of water vapor, because RH is given as 5%, which is equal to 0.05. RH is equal to PV by PS at dBT, implies PV is equal to, what is saturation pressure at a dry bulb temperature of 20? It is given as 2.34 into 0.05 kilopascals, which comes to 0.115 kilopascal. Once we get the PV, the dew point temperature of air is Tsat at PV. In the table it is given for .10 at PV of 0.115 kilopascal. In the table it is given that at 0.10 kilopascal Tsat is minus 15 degrees centigrade. At 0.26 kilopascal Tsat is minus 10 degrees centigrade. Therefore, Tsat at 0.115 kilopascal is equal to minus 14.5 degrees centigrade. This is the answer. Hence the problem.